In 2023, frontier machine intelligence transitioned from a remote service into a local asset that users could execute on their own hardware. For the first several years of the generative AI era, every prompt and every generated token traveled physically to a remote server facility and back. This reliance on the cloud created a rigid set of constraints: systemic latency, per-token billing, and the constant risk that a provider might deprecate an API without notice. The shift toward local execution began when researchers and privacy-focused enterprises required on-machine processing, a move that rendered legacy, cloud-optimized file formats impractical. Reclaiming that intelligence meant re-engineering the way a neural network is packaged, ensuring the model could survive within the limited memory and compute of a consumer device. Traditional training formats, like PyTorch binaries, were built for the standardized environment of a data center, not for the varied hardware of a local laptop. These legacy formats rely on a fragile network of satellite files, external tokenizers, and configuration rules that frequently drift out of sync with the core weights. The GGUF format solved this fragmentation by consolidating everything into a single, self-describing, and versioned container. Internally, the file is stratified. Above the raw weights sit a metadata dictionary and a specific padding layer, aligning the data on a 32-byte grid. This alignment allows modern processors to fetch weights directly from memory, without the performance stalls caused by misaligned data boundaries. A processor-aligned, self-contained file is the baseline requirement for mapping a massive intelligence into a small machine. Local inference faces a hard mathematical wall. An 8 billion parameter model at full precision requires 16 gigabytes of VRAM. That occupies the entire memory budget of a high-end laptop before the first token is even processed. GGUF subverts this hardware limit using a system call known as memory mapping, or mmap. Rather than loading the whole file into RAM, the operating system maps the model into virtual memory. Tensors are paged into physical memory only when the model demands them. This kernel-managed paging allows a neural network to execute, even if the file size exceeds the machine's physical RAM. While memory mapping prevents the system from crashing, generating text at usable speeds requires mathematically shrinking the model's footprint. That shrinkage is achieved through post-training quantization, taking a continuous floating point weight and scaling it down to a small integer, like 4 bits. Naive linear quantization treats every weight in the network the same way, which quickly leads to a total loss of model coherence. Neural networks are top-heavy structures. A small number of extreme outlier weights, mostly inside the attention mechanism, control the model's logic. When a rigid grid flattens these outliers, it destroys the model's reasoning. The resulting model might be small enough to fit on a phone, but it loses the ability to form coherent sentences or follow complex instructions. K-quants addressed this by using architectural intuition. They isolate sensitive layers to stay at high precision while aggressively crushing the resilient feed-forward networks. This move established that effective compression is a surgical process, identifying and protecting the specific weights that define the model's behavior. Manual intuition provided the first step, but achieving higher efficiency required letting the network identify its own critical paths. By running a calibration dataset through the network, developers can directly observe which individual weights have the greatest impact on the final output. This generates an importance matrix, an empirical, topological heat map of the specific parameters that drive the model's predictions. iQuants use this map to push the compression floor lower, safely collapsing low-importance weights to as little as 1.5 bits. This data-driven profiling allows a 32 billion parameter model to fit into 13 gigabytes of memory, bringing workstation-class intelligence to a standard laptop. Unsloth Dynamic 2.0 took this a step further by abandoning fixed bit widths for the entire model. The system focuses on KL divergence, a mathematical measurement of the statistical drift between the compressed output and the original model. The system tests multiple candidate bit widths for every individual layer, choosing the specific precision that minimizes drift while maximizing space savings. The result is an organic compression profile. No two layers are necessarily the same, mixing 3-bit, 5-bit, and nonlinear formats block by block. These sub-4-bit models are so efficient they can match the performance of the original uncompressed weights within a single percentage point. By managing statistical drift at the layer level, the community found the mathematical limit of compression, clearing the way to address the physical reality of hardware. This is where statistical math meets physical hardware. Those optimized weights must be moved across the machine's memory bus. To generate just one token, the entire multi-gigabyte model must be streamed from memory to the compute cores. This happens once for every single token produced. During text generation, your processor is mostly idle. It spends 98% of its time waiting for the memory bus to deliver the next batch of weights. Memory bandwidth, not raw mathematical throughput, is the absolute ceiling on local inference speed. Every bit saved through compression is a bit that doesn't have to travel across the bus. Smaller models don't just save space, they physically accelerate the hardware by reducing the data transfer required for every word. This bandwidth bottleneck affines the hardware landscape. NVIDIA RTX cards trade total memory capacity for an extremely wide, fast bandwidth pipe. Apple Silicon takes the opposite approach, a unified memory pool that fits larger models, but moves that data through a much narrower pipe. The GGUF engine, llama.cpp, is written in C++ to compile natively against both architectures, bypassing the overhead of standard AI software stacks. Orchestration tools like Ollama wrap this core engine, providing an accessible interface for creators to manage their own local models. The GGUF ecosystem now serves as a distribution layer for sovereign intelligence, allowing users to execute unpermissioned machine reasoning on their own hardware anywhere in the world.